My name is Alexander Schperberg, and I will be presenting our work entitled Auto-Tuning of Controller and Online Trajectory Planner for Legged Robots. I would like to thank my co-authors for their collaboration and Mitsubishi, the IROS conference, and reviewers for this opportunity. Planning and control for legged robots is challenging as there's a tight coupling of reaction forces generated by discrete foot contacts with the environment and the robot's center of mass. And for legged robots to be useful, we also expect them to traverse over unstructured terrain robustly. To provide a brief overview of past and current approaches towards planning and control of legged robots, we start with the zero moment point, which uses the linear inverted pendulum dynamics to optimize over the COM to satisfy the ZMP. It is computationally efficient, but the footsteps must be specified a priori. To provide footstep positions, body motion, gait timings under nonlinear dynamic constraints, trajectory optimization can be used. However, it is challenging to implement online and relies on good initial conditions. MPC considers simpler robot models and is useful for optimizing online footstep and body motion while also providing controlled joint torques. Adaptation to different environments and tasks may depend on the tuned cost function weights. Lastly, RL has shown very impressive results recently and can adapt to unstructured terrain while also learning complex robot dynamics while running online. The one downside is that long development time is necessary for tuning hyperparameters. We present another approach that may alleviate some of the issues of the past methods by using an auto-tuning technique that employs a common filter to estimate user-defined parameters with a training objective that recursively evaluates the performance of a closed-loop system online. Unlike Bayesian optimization, this method does not require trial and error, surrogate functions, and can handle disturbances due to the recursive nature of the algorithm, and lastly can calibrate parameters on a single run. To provide a brief overview of this technique, we assume access to some dynamic model of the system. Thus, our method is model-based. We then define some training objective, where y is considered the nominal user-specified value. You can think of this as values from a reference trajectory or even something more general, such as the desired amount of energy consumption. H is the specification function and a function of theta, where theta is any user-defined control parameter. This function is evaluated based on the given dynamic model. For example, the function may estimate the energy consumption of the system using a model of swinging the leg and must be affected by the user-defined parameter theta, such as the step height of the swing trajectory. C is a positive definite matrix which can be used to specify or rank the importance of various objectives. For example, prioritizing minimizing energy consumption over following a specified reference trajectory. Here we define the update to the user-defined parameters. These user-defined parameters can be the gains of a swing controller or height of a swing reference trajectory. We can specify k-n here to numerically show that we update these parameters episodically rather than after each time step. The update is done using the Kalman gain, where the Kalman gain is calculated using a UKF. Essentially, this implementation of a UKF differs from other UKF applications where you can think of the control parameter or theta as the states of a typical UKF, and instead of having sensor measurements as the H term, we replace it with our specification function. I now describe the overall application of our auto-tuning method. First, we assume access to some initial reference body and footstep trajectory. This trajectory may be calculated using complex TO methods or very simple methods as we do in this paper. This reference trajectory is then modified using our auto-tuning method based on our specified training objectives. The reference trajectory is also sent to a control module, which consists of a standard MPC stance controller when the foot is in contact and a PD swing controller when the foot is not in contact. Both controllers have parameters that we can tune or calibrate. This can help make simple and well-known controllers more robust to external factors or model errors. During operation, as these parameters are calibrated online, we continuously receive joint torques from our controller to move the robot, where the state of the robot is used to feed back to the planning and auto-tuning module. I will now discuss the training objectives. When the foot is in contact, we use an MPC stance controller which produces optimal forces at the foot to stabilize the robot's base. The auto-tuner requires a dynamic model, and the cost weights of the MPC are controlled parameters. The overall training objective is to calibrate these weights so that the predicted center of mass trajectory given by H is equal to the reference trajectory given by Y. For the swing controller, we use the following PD controller that outputs joint torques. The dynamic model in this case is simply based on the equation of motion, which can determine the joint positions and velocities. The control parameters are the Kp and Kd gains of the swing controller. The objective, as before, is trying to equate the reference trajectory given by Y with the predicted footstep positions and velocities given by H. We also calibrate the reference trajectory for the body and footstep motions. Our references are generated using desired velocity. We use the same dynamic model as for the swing controller, For calibrating this reference trajectory, we use step clearance during the motion of the swinging leg and the velocity of the robot's body or forward progress. For the training objectives, we want the predicted velocity given by hv to match our desired velocity. And second, we want the predicted step clearance given by hz to match the desired step clearance. We also consider trying to produce reference trajectories that help minimize slippage. To minimize slipping, the z-axis of the force should dominate over the x and y terms. Thus, our desired value for hf is 0. Our last training objective is the energy consumption. This can simply be calculated by setting he to be the following. Since we want to minimize the amount of energy consumption, we set y to 0. Thus, we can combine all control and reference trajectory parameters towards a single unified framework. Here we show our results when calibrating only the MPC stance and PD swing controllers. We start with bad initial gains and let the autotuner calibrate these gains during operation. On the left video, we use the autotuner to calibrate the gains, enabling the robot to continuously walk, while on the right video, we do not use any autotuning and the robot quickly falls. Here we show our results when calibrating the reference trajectory directly, considering as training objectives improving walking speed, increasing foot clearance, minimizing foot slippage, and minimizing energy consumption. We also show the robot moving along unstructured environments using the calibrated gains. Note, we do not use any vision nor consider obstacles during trajectory planning. The robot is traversing this terrain completely blind. For future work, we would like to anticipate modifying trajectories using vision and auto-tuning. Thank you for listening.